Zoe's and Michelle's Math Hour!
Hello friends, Michelle and I are here, or not here as the case may be, to talk about the derivatives of inverse trigonometric functions. Believe me, that sounded a lot more complicated than it actually is.
You will see a couple of these problems on the AP test, but not many. So it's probably wise to at least watch these videos to understand this concept fully.
Now to start off, you must know that trigonometric functions do not have inverse functions across the whole domain. But some sections of these functions are one-to-one and can therefore have inverse functions. But we will talk about this concept later in the video.
By the way, for this concept, you need to remember some of your trigonometric identities. Yes.
Now, to take the derivatives of the inverse trigonometric functions, we use these formulae. But how do we get these formulae? Can we prove them? Well, Michelle is here to show us.
So drawing a graph or a picture is always an important part of solving math, and it's also another way to solve the problem in an easier way. So you have to draw inverse sine function graph first in order to prove the inverse trigonometric function derivative.
Right here we're defining the domain, right?
Yeah. So if you flip that, well, that's actually a graph of sine x.
Yeah.
And if you flip that, it would be an inverse sine x graph.
We're flipping it across y equals x, right?
And then if you draw a vertical line on the graph to see whether the graph is having two y values and the same x value.
If it has two y values at the same x value, it means that it's not one-to-one.
To have a derivative of the function, it has to be a one-to-one function. So in this case, it would be necessary to set an interval for y equals sine x and inverse sine x. When the domain of the sine x is from negative pi over 2 to pi over 2, and the range of the sine x is negative 1 to 1. For inverse sine x, the domain and range of them would be flipped. So the domain would be negative 1 to 1, and the range would be negative pi over 2 to pi over 2.
Just erasing some excess graphs here. Alright, now that we've defined the domain, we have to actually start proving the derivative. So we're saying here that the inverse of sine x equals y is the same thing as sine y equals x.
And we're gonna take the derivative of the whole function, whole equation, with respect to dy. So it would be d dy sine y equals to x, which is gonna be dx dy equals to cosine y. In here we have to use trigonometric function identities, which is gonna be sine square y plus cosine square y equals to 1, and cosine square y equals to 1 minus sine square y, and that gives us cosine y equals to 1,
the
square root of 1 minus sine square y.
Yeah.
And since it is given that sine y equals to x, that will equal square root of 1 minus x squared. Now we flip dx dy, so it would be dy over dx, which is going to give us 1 over square root of 1 minus x squared. And that's the derivative of it.
Next, we're doing the inverse of tangent x. And once again, we have to define the domain. So we're drawing a graph of
Tangent
tangent x
here. And we're going to flip it.
Over y equals x.
Yeah.
And it ends up looking vertical instead of horizontal, just because we're flipping it over y equals x.
And it's actually increasing. So it won't really have a point where they have two y values at the same x value. So the domain would be negative infinity to infinity. So now we're going to actually prove the derivatives of the inverse tangent x. And we're going to take the derivative with respect to y, which is going to give us dx dy equals to secant square y. And by using the trigonometric identities here, again, we know that 1 plus tangent square y equals to secant square y. And since it is given that tangent y is x, in this case, it would be 1 plus x squared. And then we're going to flip dx dy to dy dx, which is going to give us 1 over 1 plus x squared.
And last but not least, the inverse of secant x.
So we're going to do the same thing here too. We're going to say y equals inverse secant x is the same thing as x equals secant y. And we're going to take derivative with respect to y, which is going to be dx dy equals to tangent y secant y. And we know by the trigonometric identities, tangent square y plus 1 is secant square y, and so tangent square y equals to secant square y minus 1.
We're just moving around the identities
Yeah.
here.
So the tangent y would be square root of secant square y minus 1. So we're going to substitute the 1 with a secant to the tangent y place. And since secant y equals to x here, it's x squared minus 1 inside the root, and we're gonna multiply x to it. So if we flip over that, it's gonna give us 1 over x times root x squared minus 1.
That was great, Michelle. Maybe proving these derivatives will help us understand better how to solve them. Next time we will be solving some examples, so look out for the next video. Until next time, goodbye.
Goodbye.
Oh, and before we go, if you want to prove the derivative of the inverse of cosine, use the same pattern of proving as the derivative of the inverse of sine, but don't forget your negative signs when you're using those trigonometric identities. If you want to prove the derivative of the inverse of cotangent, use the same pattern of proving as proving the derivative of the inverse of tangent. But remember, don't forget your negative signs. And last but not least, if you want to prove the derivative of the inverse of cosecant, use the same pattern of proving as you used when you proved the derivative of the inverse of secant, but once again, don't forget your negative signs. Bye!